Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to power systems engineering, and we'll continue inductance and inductive circuits. So this is part 2. So in the previous video we discussed some basic concepts related to inductance, particularly self-inductance. So in this video we'll be discussing mutual inductance. So before doing that, inductance, okay, that basically deals with, let's say we have an inductor which is basically expressed in terms of a coil of, let's say, n turns carrying a current, let's say I. Okay, so we have a magnetic flux phi. So here the self-induced EMF, that is given as L di by dt, which is equal to N d phi by dt. So self-induced EMF or self-inductance means the flux produced by the current flowing through the same particular coil, and that flux links with itself. Okay, it cuts the same coil, it is produced by the same coil and it links with itself. Okay, so this happens when everything is related to that coil only, confined to that coil only. That is self-induction with itself, no sharing. But let us say we have two coils. Okay, we have two coils of different inductance values. Okay, let's say a current I1 flows through coil L1 and a current I2 flows through coil L2. This has N1 turns, this has N2 turns. So here first thing is that there will be flux, individual fluxes which will link with themselves, that is flux of coil L1 linking with itself and flux of coil L2 linking with itself. And another thing is flux of coil 1 linking with coil 2 and flux of coil 2 linking with coil 1. Okay, this is coil 1, this is coil 2. So this sharing of flux, okay, to the neighboring coil, that will lead to the generation of another type of EMF which is called as mutually induced EMF, and that will lead to a particular value of inductance which is called as mutual inductance. It is expressed as M. So when flux of a coil links with itself and itself only, that is self-induction. Okay, and when flux of a coil links the neighboring coil, the other coil, the EMF generated due to that, that is called as mutually induced EMF. The inductance of self, flux cutting with itself, self-induction, that is called as self-inductance, and the induction associated with mutually induced EMF, that is called as mutual inductance. So the basic definition of mutual inductance is that when two coils, neighboring coils, are brought in close proximity with respect to each other, the magnetic flux of one links with the other. This leads to generation of voltage, secondary voltage it is called. Voltage, the primary voltage is one which is produced in itself, okay, the self-induced EMF, the self-induced voltage. The secondary voltage, in sense, here is the mutually induced voltage. So the voltage is generated in the neighboring coil or the second coil. This whole process is called as mutual induction. And this property of one coil which opposes change in the current flowing in the neighboring coil, that is called as mutual inductance. Self-inductance is the property which opposes change in current flowing through the same coil. But here it opposes change in current in the neighboring coil. So here what happens is that, first again I am going to repeat it. We have two coils, coil with number of turns N1, self-inductance L1, this is coil 1. Here the total flux produced by coil 1, let's say, is phi T1, which consists of two parts. First, phi 11. Phi 11 means flux of coil 1 linking with itself, that is flux produced by coil 1 linking with itself, plus phi 12, which is flux of coil 1 linking with coil 2. This is coil 1, this is coil 2, N2, self-inductance L2. So the flux produced by coil 1 which links with coil 2, that is phi 12. Here the self-induced EMF produced due to coil 1, that is equal to L1. Let's say the current flowing through coil 1 is I1 and the current flowing through coil 2 is I2. So the self-induced EMF or voltage in coil 1 is L1 dI1 by dt, which is same as N1 d phi 11 by dt. This. Okay. Similarly, here in coil 2, we will have first the total flux in coil 2 can be expressed as phi T2, which is equal to phi 22 plus phi 21. Phi 22 is flux produced by coil 2 linking with itself and itself only. Phi 21 is flux produced by coil 2 linking with coil 1. Here also there will be two types of EMF. First is the self-induced EMF in coil 2, which is equal to L2 dI2 by dt, which is equal to N2 d phi 22 by t2. Okay, this is Faraday's law and this is the inductance property of self-inductance. These two are self-induced EMFs in coil 1 and coil 2 respectively. But there is another type of EMF which will be generated, which is mutually induced EMF. So the mutually induced EMF in coil 1 will be due to the current flow in coil 2, the flux of coil 2, the current flow of coil 2 and the flux of coil 2. So here the mutually induced EMF will be given by M, mutual inductance, dI2 by dt. Okay, again pay attention, mutually induced EMF in coil 1 will be due to current flowing in coil 2 or flux of coil 2 linking with coil 1. So Vm1 can be written as M dI2 by dt or N1, number of turns of coil 1, because flux of coil 2 links with coil 1. So number of turns of coil 1 will come into play, and d phi 21 by dt, flux of coil 2 linking with coil 1, that is mutually induced EMF in coil 1. Then mutually induced EMF in coil 2 will be again M di1 by dt. Mutually induced EMF in coil 2 will be due to current flowing in coil 1 or flux produced in coil 1 linking with coil 2. So here number of turns of coil 2, flux produced in coil 1 linking with coil 2 d phi 12 by dt. Okay, so this is the concept of mutual inductance, where the current flowing in the neighboring coil, the flux produced in the neighboring coil, that comes into play. In self-induced, the current flowing in the same coil, the flux linking with the same coil with itself, that comes into play. Okay, so the expression of mutual inductance can be expressed as N2 phi 12 by I1 or N1 phi 21 by I2. Okay, from this. Okay, or Vm1 by di2 by dt or Vm2 by di1 by dt. That is the expression of mutual inductance. So this whole concept is called as the concept of coupled circuits. Okay, because the two circuits are joined together, they are coupled together. And another expression which is very important here, concept, which is the coefficient of coupling. So the coefficient of coupling basically expresses the fraction of the total flux of one coil which links with the other. Okay, the fraction of the total flux of one coil which links with the other, which contributes to mutually induced EMF. So coefficient of coupling K is basically phi for coil 1, fraction of flux of coil 1 which links with coil 2 divided by total flux of coil 1, or K can be fraction of flux of coil 2 which links with coil 1 divided by total flux of coil 2. And another alternative expression is this: mutual inductance divided by root over of the individual product of the individual self inductances, M by root over of L1 L2. Okay, this is the coefficient of coupling. So the basic definition of coefficient of coupling is the fraction of the flux of one coil which links with the neighboring coil. For coil 1, it is this portion of flux of coil 1 which links with coil 2 divided by total flux of coil 1, and portion of flux of coil 2 which links with the first coil divided by total flux of coil 2. Or in terms of mutual inductance and individual self inductances, this is M by root over of L1 L2. So here there is another important concept, which is the concept of dot convention. So why this is important? To determine the polarity of the mutually induced voltage. Now we know that the self-induced voltage will always be in a direction opposite to the changing flux. So that's why, as per Lenz's law, it is L di by dt, which is N d phi by dt, like that. But here, in case of the mutually induced EMF, it is very important to determine the direction of the polarity of the induced EMF. So there is a very simple law for that. So the mutual inductance is expressed in terms of N, and there is a convention called as dot convention which helps us to determine the polarity of the voltage. So here let's say the dots are placed here, which expresses the mutual inductance, and let's say the current is flowing in this direction. Current I is flowing in this direction. So here, if you see, for coil L1, the current is flowing into the dot, and for coil L2 also, the current is flowing into the dot. So here the direction of current flow with respect to the dot is the same for both coils. So here M will be positive. Okay, M will be positive. Let's say we use another notation. So here, let's say the dot is placed here, and here also the dot is placed here. The direction of current flow is like this. For coil L1, the current is flowing away from the dot. For coil L2 also, the current is flowing away from the dot. Same current directions with respect to the dot. Here also, M is positive. Okay. Next is, let's say the dot, one of the dots is placed here, the other dot is placed here to denote mutual inductance. And here current is flowing in this direction. So in coil L1, the current is flowing into the dot. In coil L2, it is flowing away from the dot. So different directions with respect to the dot in both the coils. So here M will be negative. Same goes here. Let's say here in this case, the dot is placed here in one case, and here the dot is placed here in another case. So here the current direction is like this again. Here in case of coil L1, the current is flowing away from the dot. In case of coil L2, it is flowing towards the dot. So here again, current flow directions, they are different with respect to the dot in both the coils. So here M will be negative. Okay, so what I'm trying to say, M is positive, M is negative, is that the expression of the the mutually induced EMF will be Vm, depending upon the polarity of the voltage, mutually induced voltage, or the sign convention of M, it will be minus, as per Lenz's law, plus minus M di by dt. Okay, that is denoted by that, depending upon the value of M as per the dot convention. Okay, so this is just basic thing. It will come into play in our discussion related to power systems. So just to have some idea about it, I just expressed. Then is the mutual inductance between two solenoids. So here basically in the first video we discussed a single solenoid coil consisting of a single core with only one type of wire wound over it. So let us imagine another situation where we have an insulated core and we have two types of wire wound closely packed, two types of wire, they are wound closely such that they have the same cross-sectional area and same length. One wire, which is denoted by the blue color, consists of N1 turns, and the second wire, which is expressed in terms of red color, has N2 turns. So when we have two different wires wound over the same core of different number of turns but closely packed, it is same as a coupled circuit. Okay, it is same as a coupled circuit, two separate inductors. So in that case there will be a mutual inductance. So that value of mutual inductance is given by mu 0 N1 N2 A by L. Okay, when the whole system is placed in air, and if it is placed in any other medium, the relative permeability of that medium will come into play. So it will be mu 0 mu r N1 N2 A by L. That is the mutual inductance, okay, of two solenoids wound very closely to each other on the same core. Next is inductance in series. So let us say we have different inductors. We are not taking into account the mutual inductance here. Simply three separate coils of inductance values, self-inductance values L1, L2 and L3 Henry. So in that case, the total equivalent inductance, series inductance, that will be equal to L1 plus L2 plus L3 up to the nth number of inductance. And if we have three inductances connected in parallel, so how do we know that it is in parallel? Because they have the same potential difference across them. How do we know that they are in series? If they have the same current flowing through them. Okay, so just to make you understand, it means, let us say they have the voltage drops V1, V2 and V3. So here V is equal to V1 plus V2 plus V3 as per KVL. So here the equivalent inductance LEQ di by dt is equal to L1 di by dt plus L2 di by dt, because the same current is flowing through them, plus L3 di by dt. If we take di by dt common, so we have L equivalent is equal to L1 plus L2 plus L3. Okay, and in case of here the parallel inductance, the same potential difference, so here KCL will come into play. Let us say we have a current, total current I, so I is equal to I1 plus I2 plus I3. So here I is equal to 1 by L equivalent integration of V dt minus phi to t, so not going into that, which is equal to 1 by L1 integration of V dt plus 1 by L2 integration of V dt, because the same potential difference across each of the inductors, plus 1 by L3 integration of V dt. So V dt is common on both sides, so this becomes 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus 1 by L3. Okay, series and parallel inductances. So for parallel, the reciprocal of the individual inductances are added together, and for series, the individual self-inductances are added together. Okay, so this is the thing.